Welcome back to the deep dive. Last time, we really dug into the why of quantum computing. Why we're pushing beyond classical machines.
Right. The limitations are becoming clearer, especially for certain types of problems.
Exactly. So today, we're tackling the big question. The how. How on earth do you build a computer that runs on rules that seem, well, frankly, bizarre compared to our everyday world?
It is bizarre, isn't it? The answer, fascinatingly, lies deep in quantum mechanics. That's the physics of the extremely small atoms, electrons, photons. Down there, the rules we're used to they just don't work the same way.
And that strange world is the engine for this new technology.
Precisely. It's the engine room. Understanding it is key.
And our source material today, which is the second article in a series on foundations and applications of the Internet of Things, really highlights this. It stresses that getting these core quantum concepts is essential to grasp the sheer potential here.
Absolutely. It's not just abstract physics. The stuff underpins technologies being actively researched and developed right now. We're talking potential breakthroughs in medicine, materials, AI, secure communications. The list's going on. Understanding the how is about understanding that future potential.
Okay, so our mission today is to break down this quantum engine.
Yeah.
We need to understand how these weird rules actually power a computer. We've got a list of key questions we want to explore. Let me see, about 14 of them.
Sounds like a good roadmap.
Yeah, we'll cover. What's the basic info unit, the qubit? What's superposition? How do we write that down with math? Alpha and beta. What's this exponential advantage people talk about? How do we get answers out if it's all probabilities? What's measurement? How do algorithms even work then? What is entanglement, that spooky action? Does it mean faster than light travel?
Ah, the big one.
Right. Then what's the Heisenberg uncertainty principle and the no cloning theorem? Why is that important for security but tricky for fixing errors? What's the block sphere for visualizing things?
It's a very useful tool.
And finally, how does it all fit together to make this engine? And how does that block sphere help picture the operations, the gates?
That's a comprehensive list. Should give us a solid foundation.
Okay, let's dive in. Question 1. We know classical computers use bits. What's the fundamental unit of information in quantum computing?
Right. So the starting point, the absolute bedrock, is the qubit, the quantum bit.
Qubit. Got it.
And while we know classical bits are simple, right, either a 0 or a 1, like a light switch, it's either on or off. There's no in between.
Binary.
Exactly. The qubit, well, it completely shatters that limitation. It operates in a whole different way.
Okay, shatters the limitation. How? This brings us straight to question 2. What is this core concept of superposition, and how does it make a qubit so different?
This is where things get really counterintuitive, but also incredibly powerful. A classical bit is either 0 or 1. A qubit, because of superposition, can be 0, it can be 1, and it can be in a combination of both states at the same time.
Both at once. How does that even work? Is it uncertain?
That's a common first thought, but no, it's not really about uncertainty in the classical sense. It's actually a definite quantum state that sort of encompasses both possibilities simultaneously.
Yeah.
People often use the analogy of a spinning coin. While it's spinning, before it lands, you could say it's neither definitively heads nor definitively tails, but it holds the potential for both.
Okay, the spinning coin helps a bit.
It helps, but like all analogies with quantum mechanics, it only goes so far. The key is that a qubit isn't just a 50-50 mix. It can exist in a weighted combination of 0 and 1.
Weighted combination. Okay, that sounds like math is coming. Question 3. The source shows the state as errors, ion flux, plus Virae. What are IR, alpha, and beta doing there?
Right. So that equation is the standard way to write down the state of a single qubit. Those symbols, IMF1, are crucial. They're called probability amplitudes.
Probability amplitudes. Different from just probabilities.
Yes, slightly. They are complex numbers, meaning they can have both a magnitude and a phase, though we often focus on the magnitude squared for probability. Essentially, I'll imagine as weights. They tell you the likelihood, the probability, of finding the qubit in the AF state, or the Uman state if you were to measure it.
Ah, okay, so they determine the odds when you finally look at the spinning coin, so to speak.
Exactly. And there's a fundamental rule. The square of the magnitude of A, written Aman, plus the square of the magnitude of Bamhan must always equal 1.
Aman plus Am1.
Correct. That's the normalization condition. All it really means is that the probabilities have to add up to 100%. When you measure the qubit, it has to be found as either 0 or 1. There's no other option. This keeps the quantum bookkeeping straight.
Got it. So one qubit can be in this blend of states, But the real power seems to come when you use more than one. Question 4. What's this exponential advantage you get with multiple qubits?
This is where quantum computing starts to show its incredible potential. Let's compare. If you have, say, 2 classical bits, they can represent one of 4 possible configurations: 0, 0, 0, 1, 10, or 11. But crucially, only one of these at any single point in time.
Right. One state at a time.
Now, take 2 qubits. Because each can be in a superposition, the 2-qubit system can exist in a superposition of all 4 of those configurations, 0, 0, 0, 1, 10, and 11 simultaneously.
All 4 at once?
All 4 at once. And this capacity, this ability to represent multiple states simultaneously, it grows exponentially as you add more qubits. If you have n qubits, the system can represent all 2 to the power of n possible classical states at the same time.
2 to the power of n. That grows fast.
Incredibly fast. This is the heart of the immense parallelism in quantum computing. While a classical computer processes states one after another, a quantum computer can, in a sense, explore many possibilities in parallel within this vast quantum state space.
I remember reading a really striking statistic about this exponential growth. Doesn't it take surprisingly few qubits to represent an almost unbelievable number of states?
It really does. The source mentions this, and it's mind-boggling. With just around 300 qubits, which isn't a huge number in the grand scheme of things we hope to build the system, could represent more classical states simultaneously than there are atoms in the known universe.
More states than atoms in the universe. With
Yeah.
300 qubits, that's hard to grasp.
It truly is. And that is why quantum computers hold the promise of tackling problems that are currently completely intractable, utterly impossible for even the most powerful classical supercomputers today, or likely ever. Problems in drug discovery, materials science, complex optimization.
Okay, that potential is huge, but it leads to a practical problem. Question 5. If the qubits are in this complex superposition exploring all these two-way possibilities, how do we actually get a useful single answer out? What happens during measurement?
Measurement. This is another point where quantum mechanics behaves very differently from our classical intuition. In our world, measuring something like checking if a switch is on or off is usually passive. You look, you get the information, the switch stays as it was.
Right. Observation doesn't usually change the thing itself.
But in the quantum world, measurement is an active and transformative event. When you measure a qubit that's in a superposition, the act of measurement itself forces the qubit to choose one of the classical basis states, either 0 or 1. The superposition is destroyed.
Destroyed. So you lose that quantum state.
You do. This is often called the collapse of the wave function.
Yeah.
The rich quantum state, that combination of at asura collapses down to just Della or just Elevent.
And the probability of which one it chooses goes back to alpha and beta.
Precisely. The qubit collapses to the state orange with a probability equal to Incher, and it collapses to the state orange with a probability of Blah. Remember, those probabilities add up to 1. So measurement is how we bridge the quantum possibility space to get a classical definite result, but it comes at the cost of losing the original superposition.
So it's inherently probabilistic. Every time you measure, you get either 0 or 1 based on those odds, and the original state is gone. This leads to question 6. If measurement is probabilistic, how can quantum algorithms reliably find the correct answer? You can't just run it once and hope you got lucky, can you?
That's a very astute question. You're right. A single measurement on a single qubit in superposition is random, governed by Orrin Arendt. You can't guarantee the outcome of one shot.
So how do algorithms overcome that?
The goal of a quantum algorithm isn't to eliminate the randomness entirely. Instead, the cleverness lies in how the algorithm manipulates those probability amplitudes, R and Arendt, before the final measurement.
Manipulates them how?
Using a sequence of carefully designed quantum operations, or quantum gates, we'll touch on those later, these operations exploit quantum phenomena like superposition and, crucially, quantum interference. Think of it like waves interfering. Sometimes they add up, constructive interference. Sometimes they cancel out, destructive interference.
Okay, interference with probabilities.
Kind of. The algorithm is designed so that the paths leading to the wrong answers interfere destructively, canceling each other out, driving their probability amplitudes, and thus their probabilities, close to 0. Meanwhile, the paths leading to the correct answer interfere constructively, amplifying its probability amplitude.
Ah, I see. So by the time you measure at the end, the odds are heavily skewed towards the right answer.
Exactly. You might still need to run the algorithm multiple times to be highly confident, but a well-designed algorithm makes the probability of measuring the correct state extremely high. And this ties back to what's sometimes called the observer effect. you can't gain information about the quantum state by measuring it without fundamentally disturbing it. The original superposition is lost in the process of getting that classical answer.
Okay, manipulating probabilities through interference. That makes sense. Now let's move on to maybe the most famous and perhaps strangest quantum phenomenon. Question 7. What is entanglement, often linked with Einstein's phrase, spooky action at a distance?
Ah, yes, entanglement. It's probably the concept that has generated the most philosophical debate and head-scratching. Einstein famously called it spookhafte Fremdwirkung because it seems so paradoxical, so counter to local realism.
Spooky action at a distance. It sounds dramatic. What is it?
At its core, entanglement is a unique type of quantum correlation. It's when two or more qubits, let's just stick with two for simplicity, become linked in such a way that their fates are intertwined no matter how far apart they are physically separated. They essentially behave as a single quantum system.
Linked fates. How so? Can you give an example?
Sure. Imagine we create a pair of entangled qubits, maybe called qubit A and qubit B. We prepare them in a specific entangled state. For instance, a state where if you measure qubit A and find it to be in the state rubbit, you instantly know with absolute certainty that if someone measures qubit B, they will find it in the state rubbit, and vice versa. If A is measured as 1, B must be 00.
So they're perfectly anti-correlated.
In this example, yes, perfectly anti-correlated. The crucial spooky part is this. Before either qubit is measured, neither A nor B has a definite state. Both are still in a superposition. But the moment one is measured, the state of the other is instantaneously determined, regardless of the distance separating them, whether it's meters or light years.
Okay, that does sound spooky. Which brings us straight to question 8. Does entanglement mean information is actually traveling faster than light? If measuring A instantly tells you about B light years away.
This is probably the single biggest misconception about entanglement. And the answer, according to our current understanding and all experiments so far, is no. Information is not transmitted faster than light via entanglement.
But how can that be? It seems like information is getting from A to B instantly.
Here's the catch. The outcome of the measurement on qubit A is completely random. If Alice measures qubit A, she gets either 0 or 1 according to the probabilities defined by the entangled state. She cannot force her qubit to be 0 or 1 to deliberately send a 0 or a 1 message to Bob, who has qubit B.
So she can't control the outcome of her measurement.
Exactly. She gets a random result. Bob, measuring his qubit B, also gets a random result. They only discover the correlation between their random results when they communicate classically, maybe over the phone or internet, and compare their findings. And that classical communication is, of course, limited by the speed of light.
Right. So you know the states are linked, but you don't know what state your partner got until you talk to them normally.
Precisely. There's no way to use entanglement alone to send a classical message faster than light. But, this is a big but, this perfectly correlated randomness is an incredibly powerful resource for quantum computation and communication.
How is it used then, if not for FTL messages?
It's fundamental to algorithms that outperform classical ones. It's also the basis for things like quantum teleportation, which teleports a quantum state, not matter, and still requires classical communication. Superdense coding, sending 2 classical bits using 1 entangled qubit. And very importantly, quantum error correction. Building and maintaining stable entanglement between many qubits is actually one of the primary engineering challenges in building large-scale, fault-tolerant quantum computers.
Okay, so incredibly useful, deeply weird, but not breaking Einstein's speed limit. Let's shift gears slightly to some fundamental limits within the quantum world itself. Question 9. What is the Heisenberg uncertainty principle?
Right, the Heisenberg uncertainty principle. Formulated by Werner Heisenberg back in 1927, it's really a cornerstone of quantum mechanics. It sets a fundamental limit on how precisely we can know certain pairs of physical properties of a particle simultaneously.
Pairs of properties? Like what?
These are called complementary variables. The most famous pair is a particle's position and its momentum, which is related to its velocity. The principle states that the more precisely you determine the particle's position, the less precisely you can simultaneously know its momentum, and vice versa.
And this isn't just because our measuring tools aren't good enough.
No, that's the key point. It's not a limitation of measurement technology. It's an inherent property of nature itself. There is a fundamental fuzziness built into the quantum world. You can trade certainty in one property for uncertainty in the other, but you can never know both with perfect simultaneous precision.
How does that play out in quantum computing?
It means that certain measurements you might want to make on a qubit will inevitably disturb other properties of that qubit in an unpredictable way. Measuring one aspect inherently randomizes another. This contributes to the challenge of controlling quantum systems and is something quantum algorithm designers always have to account for.
Another fundamental limit. Okay. What about question 10? The no-cloning theorem. This sounds important too.
It is profoundly important and, again, quite counterintuitive compared to our classical experience. The no-cloning theorem states that it is impossible to create an identical, independent copy of an arbitrary, unknown quantum state.
Impossible to copy a qubit. But we copy classical bits all the time. That's how computers work.
Exactly. In classical computing, copying information is trivial. You read the bits, zeros and ones, and write them somewhere else. Perfect replica. But you can't do that with an unknown quantum state, like a qubit in some specific superposition, SCRT plus shear beforer, where you don't know IAB crashed beforehand.
Why not? What stops you?
It comes back to measurement. To learn the exact state of the qubit, to know ion precisely enough to make a perfect copy, you would essentially have to perform a measurement. But as we discussed, measurement destroys the original superposition, collapsing it to either I's or Aryan. You can't fully read the quantum state without altering it, so any attempt to copy it inevitably fails to capture the original quantum richness or destroys the original in the process.
Wow. So you can't just quantum photocopy a qubit state. That has huge implications. Question 11. Why is this no-cloning theorem so important for quantum security, and why does it make quantum error corrections so difficult?
It cuts both ways, presenting both opportunities and challenges. Let's take security first. The no-cloning theorem is the absolute bedrock of quantum key distribution QKD protocols.
How does it help QKD?
Imagine two parties, Alice and Bob, trying to establish a secret cryptographic key using qubits. If an eavesdropper, Eve, tries to intercept the qubits Alice sends to Bob, she can't just copy the quantum state of the qubit and send the original along undisturbed. The theorem forbids it. If she tries to measure the qubit to learn about it, she inevitably disturbs its state.
And Alice and Bob can detect that disturbance.
Exactly. By checking a subset of their qubits for discrepancies caused by Eve's meddling, they can detect the presence of an eavesdropper. The laws of physics themselves guarantee that any attempt to copy the quantum information leaves detectable traces. It's fundamentally secure against this type of eavesdropping.
That's incredibly powerful for security. But what about the flip side? Why does it make error correction hard?
Well, think about how we handle errors in classical computing. A common technique is redundancy. You make multiple copies of a bit. If one copy gets flipped by noise, you can check the others and figure out the original value by majority vote.
Right, simple redundancy.
But the no-cloning theorem says you can't simply make copies of an unknown qubit state for redundancy. So classical error correction codes just don't translate directly. This presents a major challenge for building reliable, fault-tolerant quantum computers because qubits are inherently fragile and prone to errors from environmental noise.
So how do they do quantum error correction then?
It requires much more sophisticated techniques. Instead of copying, they use clever entanglement strategies to distribute the information of a single logical qubit across many physical qubits. These codes are designed so that errors affecting individual physical qubits can be detected and corrected without ever needing to measure and thus destroy the underlying logical quantum state itself. It's a very complex and active area of research.
Entanglement to the rescue again, but in a complicated way. Okay, we've covered superposition, measurement, entanglement, uncertainty, no cloning. These concepts are pretty abstract. Question 12. Is there a way to visualize what's going on, at least for a single qubit? What is the Bloch sphere?
Yes. Thankfully, there is a really elegant geometric tool for visualizing the state of a single qubit. It's called the Bloch sphere.
Bloch sphere. Okay, what does it look like?
Imagine a standard three-dimensional sphere, like a globe. We designate the very top point, the North Pole, as representing the classical state Yaris, and the very bottom point, the South Pole, represents the classical state
North Pole is 0, South Pole is 1. Got it. What about superposition?
That's the beauty of it. Any other point on the entire surface of the sphere represents a possible superposition state of the qubit. A unique point on the surface corresponds to a specific combination of the probability amplitudes after mu.
So every possible state of a single qubit is a point on this sphere's surface.
Exactly. The state can be described by two angles on the sphere, usually called theta and phi, similar to latitude and longitude on Earth. These angles directly relate to the values of octamu. It gives us a concrete, visual way to picture the vast range of possible qubit states beyond just 0 and 1.
That sounds incredibly helpful for building intuition. Okay, let's try to tie this all together. Question 13. How do all these concepts we've discussed, superposition, measurement, entanglement, uncertainty, no cloning combine to form the engine of a quantum computer.
They really are the fundamental component, the gears and pistons of this new computational engine. Let's recap. Qubits and superposition provide the raw material. They allow us to create this exponentially large computational space where we can represent two O states simultaneously.
The vast playing field.
Right. Then, the nature of probability amplitudes and measurement gives us the mechanism to interact with that space and extract meaningful answers. We manipulate probabilities using interference.
Steering towards the solution.
Exactly. Entanglement adds another layer of power, creating these non-local correlations, these intricate links between qubits that enable algorithms and operations that have no classical counterpart. It allows for complex, system-wide computations.
The spooky connection enabling new tricks.
And finally, the fundamental limits like the uncertainty principle and the no-cloning theorem define the boundaries and challenges of this quantum world. They dictate how we must interact with qubits, leading to challenges in error correction, but also enabling unique applications like quantum cryptography. Together, these principles define the operational physics of a quantum computer.
That's a great synthesis. It paints a picture of using these very non-classical rules as tools. Now, one final question, circling back to visualization. Question 14. How does the block sphere specifically help visualize quantum operations, the things algorithms actually do to qubits? You mentioned quantum gates earlier.
Yes, the block sphere isn't just for picturing static states. It's incredibly useful for visualizing the effect of quantum gates acting on a single qubit.
How so?
Essentially, any operation, any quantum gate applied to a single qubit corresponds to a rotation of its state vector on the surface of the block sphere.
A rotation. So applying a gate just moves the point representing the qubit state somewhere else on the sphere.
Precisely. For example, remember the classical states Idrios and Idro are at the north and south poles. A common and important gate is the Hadamard gate. Its function is often to create an equal superposition. Applying a Hadamard gate to a qubit initially in the ST state, at the North Pole, corresponds to rotating its state vector down to a specific point on the sphere's equator.
And points on the equator represent equal superpositions.
Yes, points exactly on the equator represent states where, if you measure, you have a 50-50 chance of getting 0 or 1. The Hadamard gate is a fundamental way to put qubits into superposition. Other gates correspond to different rotations rotating around the vertical axis, the horizontal axis, etc. It gives quantum programmers a visual intuition for how they're transforming the qubit state.
Does the position on the sphere also relate to measurement probability?
It does. As we said, North Pole is definite 0, South Pole is definite 1. The closer the state vector's point is to the North Pole, the higher the probability of measuring 0. The closer it is to the South Pole, the higher the probability of measuring 1.
That's very cool. A visual map of both state and probability.
It is. But it's crucial to remember the important caveat. The block sphere can only represent the state of a single qubit. It simply cannot capture the complex correlations involved in the state of two or more entangled qubits. Their combined state space exists in a much higher dimensional mathematical space that we can't easily visualize this way.
Ah, okay, so it's a great tool for one qubit, but entanglement breaks the simple picture.
Exactly. But despite that limitation, it remains an absolutely indispensable conceptual tool for understanding and visualizing single qubit states and operations, which are the building blocks of all quantum computation.
What a journey this has been. We've gone from the basic qubit through superposition, entanglement, these deep physical limits, and even a way to visualize it. The principles of quantum mechanics, they really do paint a picture of a reality that's just fundamentally different from what we see around us every day.
It's a world where particles can indeed be in multiple states at once, where just looking changes the outcome, and where distant objects can have this strange, intimate connection.
And the amazing thing is you've shown us these aren't just weird ideas for physicists to ponder. They are the actual practical nuts and bolts, the engine that's driving this entirely new generation of computing technology. It's really happening.
It really is. And perhaps a final thought to leave you with. As our ability to engineer and control these quantum phenomena continues to improve phenomena, we can partly visualize with tools like the block sphere. We get closer and closer to building quantum machines that won't just solve problems faster, but will fundamentally redefine the boundaries of what problems are solvable at all.
Redefining the boundaries of the possible. That's a powerful idea. What kinds of discoveries or innovations might that unlock? It's exciting and maybe a little daunting to think about.
It truly is. The full impact is hard to predict, but it spans across science, technology, and perhaps even our understanding of information itself.
Well, thank you for guiding us through that complex quantum engine room, and thank you for joining us on this deep dive. To keep exploring the frontiers of technology with us, please be sure to subscribe to Tech, AI, and Beyond.
Thanks for the great questions. It was a fascinating discussion.
We'll see you next time.